Okay, so welcome back to Unit 3. So we're continuing to talk about electric circuits. Here we're going to focus on the concept of power, okay? It's something that we talked about when we did do energy, when you do that work energy power unit back in mechanics, but now we're going to relate it to electric circuits and electric power, okay? This is where you get, the wattage of light bulbs, okay? And so just remember that power is the rate at which energy is transferred. Okay. Now when we did talk about it in the work energy power unit in mechanics, we talked a lot about that powers work over time. But remember, work is a transfer of energy, right? And so we can just say power equals the change in energy over the change in time. You can also write it as a derivative, right? So power is dE dt. When we talked about it in the WEP unit, we did power equals work over time, right? And so you can just say, remember, power is something over time, okay? Now, electrical power, which, by the way, is still given the same unit of P, right, is the rate per unit time in which electrical energy is transferred by an electric circuit. So remember when we talked about when we know there is a flow of electrons, we said that the wire gets heated up, okay? This is one of the reasons why the wire is heated up, right? It's because there's a transfer of power, okay? And so remember, power is measured in watts, and it's given by the formula in terms of electrical power, P equals IV. Now, when we talk about it in respect to electrical units, right, 1 watt is 1 volt amp, okay? And remember, from energy, we said it was a joule per second, but because we're talking about in terms of current and potential difference, it's 1 volt amp. So one thing to note is that as an electron moves through a resistor at a constant drift speed, its average kinetic energy remains constant, and its lost electrical power appears as thermal energy. Remember we talked about one of the reasons why we know there's electrons flowing is that the wire is getting warm, right? Or the resistor or so forth is getting warm. Okay, so the mechanical energy thus transferred to thermal energy is dissipated, right? Is given off. That's what kind of what dissipated, remember, means, right? Or lost because the transfer cannot be reversed. So using R equals VI, the Ohm's law relationship, we can derive 2 other equations for power. So power is I squared R, and all I simply did was I took, if P is IV, okay, I solved this for V, and so I get V equals IR, so I'd say, okay, I times IR, and that's where I get the I squared R from, okay? And so that is one version of power, okay? And then another version is V squared over R, because again, if I take power, I got IV, and I substitute, and now I'm going to set this equal to I, which is V over R. So I get V over R times V, and I get V squared over R. Right? So we can write these equations related to voltage and resistance and current and resistance. But one thing to note is that P equals IV, kind of the original equation that we talked about, applies to electrical energy transfers of all kinds. But this I squared R and V squared R apply only when you're changing from the electric potential energy to thermal energy in a device. Okay. Again, if you took like AP Physics 1, when you did do circuits, if you took an on-level type course, we just kind of lump these 3 versions of the equation together, and we don't make that distinction. Okay. Now, let's look at an example. It says, talking about you're given a length and uniform heating wire made from nickel chromium iron alloy called nichrome. It has a resistance of 72 ohms, at which rate is energy dissipated in each of the following situations. A potential difference of 120 volts is applied across the full length of the wire, and then the wire is cut in half, and a potential difference of 120 volts is applied across the length of each. Okay, so first part of the question is pretty simple. We're going to do P equals V squared over R. We know we can use this equation because it talks about it's a heating wire, right? And so remember, we're talking about we can use these equations when we transfer the electric potential energy to thermal energy. And so all I'm going to do is 120 volts squared over 72 ohms, and that's going to give me 200 watts, right? And so that means there's 200 joules transferred every second, or 200 volts, volt amps, okay? Now, the second part is just kind of a little strange, right? Because we've never talked about what happens when we cut resistors in half or quartered. So one thing to know, if we go back to the resistance formula, right? So R equals rho LA. Note that R and L have a direct relationship. So in this case, if I cut the wire in half, what happens is I cut my resistance in half. So if I cut this in half, this also gets cut in half. So that means in each wire, the resistance, or I'm going to call it R sub N or R new, is just going to be half of our original. So it's going to be 36 ohms, right? And now I can use the equation because I have the same potential difference. So my new power dissipated is going to be V squared over my new resistance. And so I'm just going to do V squared, which is 120 squared over 36. And you can see it's going to be 400 watts, right? So it's going to be 400 joules transferred. You can also do this using the factors of 1, right? Knowing that these two have a direct relationship. So what is my new power if I keep my voltage the same, but I cut my resistance in half? And so I got 1 over 1/2, which tells me that my new power, right, is going to be double my old one, right? And here's our old one, P old, right, or P original. And so we know that the new power is going to be double our old one, okay? And so you can see that it popped up right here with 400 watts. All right, so in the next video, we're going to dive into what are called series and parallel circuits, and really focusing around resistors in those circuits.